Differential notations in first principle. This is the y-axis and that's the x-axis. The y-axis is also called f of x. And that's the x. This could be velocity, this could be time. Y and x are just default letters. We are looking for the derivative of y with respect to x. So this is the derivative of y with respect to x. Naturally, you pick a point there and another point there. We need to know that the gradient is changing along this curve because it's variable. So the gradients are always changing. It's never the same. So this one is the initial value. So that's your x. That's your x, initial value. And this is your final value. We call that x plus delta x. So that's what we call that because this is a final value, this is an initial value. And likewise, that coordinate will have the y coordinate. That's your y. And this one too will have the y coordinate for y plus delta y. So delta means small change. Because the gradient is changing along as you go along the curve, it's never the same. It's very difficult to find the derivative or the gradient of this curve. The only time to find the actual gradient of this curve is to find at a particular point. So because we're not doing that, that's why we're using the notation delta y over delta x. Delta y is being used because we are actually not finding the gradient at a particular point. The coordinates here will be x plus delta x and y plus delta y. And the coordinate here will be x and y. So that is the final y value and that's the final x value. This is the initial y value, that's the initial x value. So the difference between these 2 points, how it's changing, that difference, if we measure that distance from there to there, because if we take away the initial from the final, we get delta x, right? Likewise, if we measure the distance from there to there, if we take away the initial from final, we get delta y. So we're using this notation here, delta, and delta in this case just means change. But because we're using a small delta here, so that implies the delta here implies small change. Now, to find a gradient, it's always the height over the length. Height over the length. So that's what we're looking for. We're looking for the height over the length. And that's the gradient here. But if we bring that point down as much as possible, we keep bringing that point or bring that to a point where it becomes so small, the difference between these two, infinitesimally small. So we can then maybe produce a point like that. And that point is what we then called, well, we draw a tangent to that point. So that's a tangent. And then, so what happens is we bring these 2 points close so that the difference between the two is so small. And then we then pick a point along those two and actually find the gradient. Because the gradient on each curve the gradient on each point is different. That gradient is not going to be called small delta anymore. It will be called capital delta. So the difference, if that was x, and that would be x plus dx. Not delta, but dx. Sometimes d is written as x plus capital delta x. So that's the same thing. Now we can do that because we brought those 2 points together to form that tiny point, and then we draw a tangent to that point, and now we can find the gradient here. So the coordinate here will be x plus dx, not delta, but d, and y plus dy. And the coordinate here will be x and y. So that will be y here. And that will be y plus dy. So that's the difference between the small delta and the capital delta. When we then use in the limit, we said delta x would tend to 0. And that implies that dy dx, delta y over delta x, would tend to dy over dx. So that's why we use the limit. That means we bring the difference between the two so small that this difference, dx, becomes really small. And that's what that meant. That's what the limitation implies. So these are called differentials. Dy and dx are called differentials. So if I say delta y or dy, let's just call dy, and dx are called differentials. Now, the difference, this is the highest value, this is the lowest value. The difference between that and that, it's called over the difference between that and that is called the rate of change. So when we have the difference between that and the higher, take away the lowest, so that minus that is the rate of change over, which is the difference between that and that over the difference between that and that, are called the rate of change. So the y dx, because that's what you get. If you take away that from that, you get the y, and divide it by the difference between that, and that is called the rate of change. How quickly that change is happening between y relative to x. This could be velocity and time, so rate of change of velocity over time. Rate of change of displacement over time. And so that's why we talk about rate of change in applications. So the notations that are really important here are, we start off with, whenever we have y as a function of x, we can say that dy over dx can be written as y dot, same thing, or you might see y dash, that's the power there, it's a dash, or the superscript, or you might see f dash x, all mean the same thing, or you might see, let me just write that again, capital delta, that's a capital delta, y over capital delta of x, or you might see y2 minus y1 over x2 minus x1. So this is y2, this is y1, because the point here is 0.1, and that's 0.2. So y1 y2 minus y1. So that could be y2 and that could be y1. The same thing, because you're taking the difference. Hence the word difference. Difference means take away. And you might see y final minus y initial over x final minus x initial. Or you might see f of x plus delta x minus f of x over delta x. But don't forget delta x, or you might see f of h minus f of x over h. So that's actually pretty common, the f of h. In a lot of textbooks, you will see f of x plus h minus f of x over h. Obviously, they will put the limit here where h tends to 0. So you might see that. So those are the notations that comes with differentials here. So this is very common in some textbooks. And this one here is the classical method. But the limit, in the limit, it's implying that the difference between these two are so small. And then you get up to a point. Now you can then find the gradient. And the difference between that and that will give you that height here. So that height and that height will be dy. And this length here, the difference will be dx. So that's where that comes from. That's how you get your dy dx, with the limitation that the difference between that and that is so small that you can get dy dx. So that difference here is dy, and this is dx. Sometimes, as I said, the small difference here is called h, and that's where you can see h being used in the formula. So this expression dy dx is called the derivative of y with respect to x. So that's what we call that. That's derivative of y with respect to x. But the important thing also, the important to remember is that the d over dx is operating on y. So that's operating on y. So therefore, you can actually write it as d over dx operating on y. So this d over dx in this case is called an operator. So the whole thing here, if I just write it like that, so if I just say d over dx is an operator because it's operating on y. So that's why you can do that differentiation. You differentiating on y with respect to x. You could be differentiating y with respect to t. You could be differentiating v with respect to t. You could be differentiating the v with respect to r, the radius. So that could be the volume, and that could be the radius r. Or that could be a, the area, and that could be the radius r. That could be distance against time. So you could use the rate of change on anything. Y and x are just arbitrary, so they're just the default in this case.